Welcome to part 3 of the AE Solutions Risk Assessment webinar series, Best Practices to Ensure My Risk Assessment is Trustworthy. Just to do a quick recap of parts 1 and 2, primarily involved describing risk and models and/or equations to calculate risk. And in this context, we're talking about a likelihood component of risk. So frequency and/or probability related to risk, not necessarily the consequence modeling or consequence aspects of risk, but likelihood in terms of frequency and/or probability and of some future event, and which is important, and I'll be that'll be a common theme of today's webinar, is discussing that aspect of risk as involving a future event and the forward arrow of time. Some of the models that were presented in part 1 and 2 of the webinar series were shown here. You can see I've included LOPA and QRA, quantitative bow tie, risk-based facility siting, SILCALCs, human reliability assessment, risk-based inspection, reliability center maintenance. All of these models involve some determination of likelihood, frequency, and/or probability. And I've included LOPA here specifically because LOPA is the new QRA. And so it's important to cover that aspect of it. We're doing things with LOPA that are much closer to QRA than were, I think, envisioned in the original LOPA methodology. So we have included it here. Within each of these models that we develop to calculate the likelihood of risk, we use parameters. I'll have a slide dedicated to parameters. We feed data into the parameters. Typically, these are going to be generic point values, is what we've historically done. We'll focus on the uncertainty here in the data, in the parameters. Of course, models contain other types of uncertainty, but I want to address the uncertainty in data specifically in this webinar. We asked the general question, how trustworthy are the results? Okay. So let's first answer the question what it means to be trustworthy. And there's some dictionary definitions of here, just some dictionary words: believable, dependable, credible, certain or uncertain, reliable, confident. And each of these qualitative words has a quantitative, can be described quantitatively. As a proxy to the qualitative word. That's going to be another common theme of the presentation, is turning the qualitative into quantitative. That'll be a part of this. And now I want to spend the next couple of slides discussing an issue that has come up, question really that's came up in the part 1 of the webinar. And I've had this exact question, that exact same question asked, doing a similar webinar on Bayesian statistics. The question is, what is probability? What is meant by probability? If you don't have that question, I would be sure that by the end of this, you'll be thinking, well, don't we calculate a probability of failure on demand? Don't we calculate a probability that's part of our reliability work or availability work? And how is this probability different? And you'll eventually, if you are studying this stuff long enough and using it, you'll come up with that question. So let's just make a shortcut to it. Now, before I answer that, let's go through a couple of these proxies for trustworthiness. I want to highlight maybe here the word dependable. This word sometimes associated with IPLs or independent protection layers. Quantitatively, we can say the IPL is dependable when it has some availability. That's actually a mathematical calculation, very similar to what was presented in webinars 1 and 2. And specifically, it's a probability of a device or some equipment working at time t. The complement of that, of course, is unavailability or probability of failure on demand. We normally associate it with that. Another proxy here for trustworthiness, we would say, is reliability, which is the probability of survival beyond time t. That's also a probability that we could use to define trustworthiness and to quantify it. And so really all of these words here with their own quantitative proxies can be used to somehow get at the idea of trustworthiness. And these are things we already have in our toolkit, on our tool belt, that we can use. Now, let me drill this point a little bit further, and let me talk about the other terms that are up here. Believability, okay, if something is believable, we might say that's associated with a subjective degree of belief. That's also a probability, and any decision we make, any choice we make, any judgment we make is very, very rarely, a 0 or 100% type of confidence in the choice or judgment. And so there's always some subjective uncertainty with whatever we're selecting or judging. That's referred to in general as a subjective degree of belief. That's a probability. And that's a very interesting type because that is, like I said, subjective, and we're going to talk about that word more. But it's implicit in your mind, and one of the things we want to try to do is make that implicit subjective probability explicit, and there's a specific way to do that we'll talk about today. Now, the next couple of words here, let me go to the word uncertainty. We'll use that word instead of certain. We'll say uncertainty. That's also a probability. And the expression of uncertainty through what we might call credible intervals, or also confidence intervals. So credible intervals and confidence intervals are a way to express uncertainty. And you'll see that that's primarily what we're going to be talking about today. And those are also probabilities. All these bullets are probabilities. So you can, and there's other types of probabilities. There's a probability associated with long run frequencies, for example. And there's other types of probabilities that I haven't defined here, just FYI. But the point is, we can group these. We can group these 6 proxies for trustworthiness into 2 groups. So one group, highlighted yellow, represent physical parameters in nature. And so, for example, in webinar 1, Joe VC was asked what probability is in webinar 1. Joe VC, my colleague at AE Solutions, a very capable quantifier, and he said it's a challenge, and he's absolutely right. In the context of his webinar, probability was mostly aligned with what you would call a challenge, a physical challenge on a system, and which is what he was describing in his equations. And then the other group represented here that I have circled in red is something different. Those describe the uncertainty associated with a physical parameter, and they're also probabilities. Okay, so we have probabilities that represent physical processes in nature, like reliability, like availability, unavailability, and then we have probabilities that describe the uncertainty of those physical parameters. And so that distinction is very important to understand, even to begin to wade into this. Okay, so let me now define probability specifically for our discussion today, and just very quickly here, statisticians use probability to understand and to quantify certainty. That's one quote here. Probability, and another one is probability is a mathematical language for quantifying uncertainty. That's how we will use probability, the word probability, in this webinar. Okay, and that's fine. And specifically, we're going to use uncertainty distributions to make inferences on models, more specifically on the parameters in those models. I'll have a slide dedicated to parameters as well. But you can kind of see as we're getting in this, it's not just like jumping in and okay, let's start to grab numbers and plug them in. I mean, there's a lot of background here. And you have to be careful about how you define things and how you think about things and what you're thinking about as you create these calculations. Now, so you may be wondering, well, what is uncertainty? So uncertainty is a probability, okay, but that doesn't help me. Reliability is a probability, availability is a probability. Those have specific meanings like we saw, the survival, to time t, the probability you're working at time t, et cetera. Well, let's look at what uncertainty is just in words. Uncertainty means you cannot know the answer for sure. Another definition of uncertainty is it is risk that is hard to measure. So there's maybe a distinction between risk and uncertainty. And then another definition is, and it's an English word, what it means depends on who you ask. And so this third definition here by Dr. Lennox reveals the real nature of uncertainty. And also probability, because probability then is a measure of the uncertainty. There's two types, and they're a continuum, so they're not in two discrete buckets, but it's a continuum. There's what's known as aleatory uncertainty and then epistemic uncertainty. And aleatory is considered objective, epistemic is subjective, so it's more of that. When we talked about the subjective degree of belief, right? You're on that end of the spectrum. A good analogy here to think about is like if you had a pair of dice and you knew that they were fair, okay, and the only uncertainty associated with rolling those dice was which of the 6 sides they would land on. That's purely aleatory. That's cut into physical nature. So there's uncertainty, but it's due to pure randomness of the throw and the construction of the die. But let's say you had a pair of dice and you didn't know they were fair, and you maybe suspected that they weren't fair. This would be more epistemic ignorance, and the fact that you didn't know, you did not know if they were fair or not, and that would affect obviously the uncertainty of the throw more so than if you had known that they were fair. And so the concept here is knowing reduces uncertainty. Anytime you can gain knowledge, gain information about some aspect you're studying and trying to understand the risk, you are reducing uncertainty, and that's such an important point here, and will be key to our discussion as we go forward. So it doesn't get any more clear, and in fact, it gets a little worse. We'll see in some future slides. So probability as a proxy of uncertainty is both subjective and objective. Okay, so the question, this all began with what is probability? It is not any. It is a deep way to question, and goes to some very fundamental things in nature about what we believe and how we gain knowledge and how we know things, which is epistemology. So anyway, hopefully that I didn't make that clear as mud. Let us continue. Okay, why addressing data uncertainty? So now we kind of understand what uncertainty matters, what uncertainty is, and how we represent it quantitatively through probability. Why does it matter? Okay, better decision making. Okay, I'm going to have some examples of that. I have a whole slide of better decision making. So the methods I'm going to show you today, how does it make us? How does it help us make better decisions? What kind of decisions? It makes the numbers more believable. So in terms of context, in the context of using these numbers, I mentioned LOPA already. There's a lot of skepticism around the numbers, especially these rare event numbers that are being used, the 10 to minus 5, 10 to minus 6, right? Another reason is the risk targets that we use, the TMELs, et cetera, in LOPA, they're real world. So they're not some, now all data is contextual, all probability is conditional, but those targets are intended to represent, again, a physical parameter in the world that your expectation of a physical process is this is how safe we are. It's not some relative count on your fingers, count in your mind term. Those are intended to be real absolute numbers, recognizing there's no absolute numbers. There's always context and condition, but the targets are real world. And that's another reason uncertainty matters. How close to the edge are we operating? Another point here, the next one, data is in the past. Risk uncertainty is in the future. So this is another common theme that we're going to talk about today. It doesn't make sense to ask a question about the probability of an event in the past. It's not a meaningful question. The event has already happened, or it hasn't. So when you look at that in the past, asking about probability for the past is not a meaningful way. Probability only makes sense in the future, represented by uncertainty, whether something will happen or not. And so that is very powerful aspect of understanding the uncertainty. And in fact, PSM and reliability center maintenance, those are intended to be forward-looking, with a forward arrow of time, forward-looking methodologies. And so uncertainty has to be a part of that, because again, it represents looking a little bit into the future. Okay, and I'll talk a little bit more about that later on. Being conservative is expensive versus being correct. Do we want to be conservative or be correct? Sometimes it's okay to be conservative. Okay, there's money in the budget, whatnot, but boy, there's a whole lot of times where this really comes up, and you know, we have opportunities here, and I have some examples of that. Being conservative without putting any work in does not reduce uncertainty. So if you're not actually gaining information, gaining knowledge about a potential event, a future event, just choosing a conservative number doesn't reduce your uncertainty. It just means maybe you're spending more money. Maybe you're having to shut down more often to test. And that's certainly not making you safer anyway. The whole movement of data science and analytics, especially related to predictive maintenance, is having the same problems with not accounting for uncertainty and the problem of data, very similar to what we're seeing here and what I'm presenting today. And so if we can improve in this area, when these things come to process safety, and they are coming, predictive analytics, it's going to make it that much easier to transition into. And lastly, the standard requires it of us. I think we all know what standard we're talking about. The functional safety standards asks us to compare our assumed reliability parameters with actual. And the only way to do this is to really address it through the concept of uncertainty associated with your assumed parameter versus what you find actually in the field. Now, to properly do this, as it says here, we need to use some statistics. So this is not a meme about data science. This is a meme about me as a functional safety person, as a QRA quant. So you could easily replace data science with, you know, a quant calculator, functional safety, silk, you know, a silk calculator. We have all these models, and we're creating all these different ways to describe risk, and all of our fancy models and all the parameters we put into them, but we feed into them junk, and that's represented by the statistics here. And you know, and this is what we've done for decades now in functional safety, and now, you know, it's being propagated in LOPA. The same concept is, at some point we're going to have to, you know, say, well, you know, enough is enough, and we're going to have to really engage and try to get better at having some ability and some capabilities and statistics to help us validate, confirm the data we're using, and then we're plugging into all of our models to assess risk. That's what this means. So don't be this guy. And this is where I'm going to be talking some statistics today. So you know, it's not pretty at times. So just be aware of that. All right, so this is the standard, and it's been there for a long time, this clause, and it asks us to assess whether the reliability parameters of our sys are in accordance with those assumed during design. It asks us to compare. This one's talking about demand rates. The third bullet down here is asking us to compare demand rates. And it's even asking us if the failure rates are greater than what was assumed during design. Well, gosh, how are you going to figure that out? And so this is actually the standard requiring us to do this. And the reliability parameters, I take that to mean colloquially. That just doesn't mean failure rate. That means any reliability parameter you might use in the equation. And like I said, I got a slide on parameters that we use, and it's a lot. We use a lot of parameters in our equations, and there's a lot of potential for uncertainty there. But this clause is so far off the radar. This is not shown on any life cycle workflow chart. I never hear this being discussed how to do this. And so this is one of the things we're looking at today. Now, as a sneak peek, this is kind of the big reveal here in the middle of the slideshow. How do we compare and assess our design data to actual data? Well, we're going to have, what we do is we take our generic data that we've assumed in design from our generic data tables, and some are better than others. You may have a great generic data table from your company that's collected all kinds of data from around your sites, and you really trust it, and that's awesome. But you still need to make some site determination and make that comparison to have some confidence that at that site, yeah, you are aligned with that generic data. And so we're going to use something called Bayes' rule or Bayesian inference to compare site data and the prior data, which is your generic. And the idea is, as we run these Bayesian updates over time, as we're collecting data, we're going to develop, hopefully, an increase in confidence in the parameter. So we're not actually changing the parameter. We're not changing the number. We're building confidence. We're reducing uncertainty of the parameter. So that's the concept here. That's just kind of the big reveal to kind of show you where we are going with this. And the parameter, as it kind of comes into focus and gets bolder, means you've got more confidence, good or bad. I mean, it can go both ways, but that's the idea of what we're doing here, at least to start out. We're not asking you to recalculate a new average or a new failure rate and then redo all your calculations, all your SIL calcs. That's not what we're doing here. We're focusing on getting a better handle on the uncertainty of the parameter. Okay, parameters. You can see this slide. We have a lot of them, and we have frequencies, probabilities of failure, frequencies in terms of initiating event frequencies, failure rates, human error, the big four, demand tracking, failure rates, time and bypass, on-time testing. All of these parameters that could fit into some of our equations are at play for describing with not just point values, which is where we are now, but with probability or uncertainty distributions. I'll use those terms to mean the same thing in this context, like I said. Okay. Generic failure, the good. There's a lot of it. There's a large N. We'll talk about what N is in a few slides. It's in good agreement in general. It doesn't vary much. It varies by less than an order of magnitude between different sources of generic data. That's generally been, I've seen that stated many times, many places. So it's trusted. Like I say, especially if you work for a large company and you're collecting your own data, boy, you got it. That's great. Can be used to make relative comparisons, so of designs and et cetera, right? It's good for relative comparisons, not absolute comparisons. Like I mentioned, our expectation of we're down to 10 minus 3, 10 minus 4, 10 minus 5 at our site, in our process, in our unit, right? That's what the TML is intended to represent. If it's just intended to represent an average, that is okay because it's still conditional, but don't forget about that part of it. It allows us to get started. Okay. They're not so good. It's generic. Is it representative of your site? It's conservative. That's the bleep, but maybe not. So see above. Okay, we don't really know. And there's that word again, knowing, that sense of being able to reduce uncertainty through knowing. There's always one-off devices not covered by generic data. That happens. That comes up all the time. And the data is old. It could be way in the past. It could be 50 years old. Generally, it's going to provide point values, not parameters used to characterize distributions. And a big one here is the full potential of reliability center and maintenance is not being realized if we're just staying with generic data. And so it goes back to that concept of just being able to make relative comparisons. You're not getting that more absolute aspect of it, and making decisions regarding risk and your maintenance program and optimizing it. Okay, but the good part is it is the starting point. So we would say it's a default or null position to compare with actual data. So we know there's a lot of effort put into generic data from wherever it comes from, and we trust it, and we should trust it, but it's a starting point, but it could be our null or default position with a lot of inertia. So one of the things I want to stress here is, again, that generic data has got inertia initially. You're not just collecting a single sample. You say, oh, we got to change this. We got to redo all our calcs, and that's not what's happening here. This is a longer term process where you're building a case to prove or disprove a null or default position. So that kind of sounds like hypothesis testing. Kind of sounds like a little statistics there. Starting to develop. And speaking about statistics, there are two types of statistics: frequentist versus Bayesian. Now, if you don't know that there's different types of statistics, or even what types of statistics you're using, this may be a little bit, kind of disconcerting. But it's something. It's a bridge that has to be crossed if we're going to do this properly, including potential data analytics and machine learning applied to maintenance and ultimately applied to safety, because they are correlated, of course. I would bet that most of us are frequentists. We've been raised frequentists. I'm going to point out a few frequentist statistical techniques you're probably using today without even knowing it. The point is to know the kind of statistics you're doing, what they mean. And that's an important part of making the correct decisions based on the numbers that we'll be generating. Okay. A word about subjective probability, because Bayesian statistics is subjective. Engineers hate this because it's subjective, but subjective just means dependent on human judgment. All of process safety is dependent on that, every bit of it, and it goes back to that degree of belief when we make decisions and judgments and choices. There's always a degree of belief. Very, very rarely are things 100% or 0%. There's always that implicit probability involved in decisions. It does not mean arbitrary and non-rigorous. Examples. So here's a good example from Lopaland, a 1 in 10 year event. Now you can say, well, it's a number, it's objective. And I'm not even talking about the uncertainty in the number, a generic number applied to your specific process, maybe an initiating event frequency, which could be way more frequent than that or way less frequent than that. How do we know? Well, we have to put some work in to find out. But anyway, so I'm not talking about that. I'm just talking about how you subjectively interpret the number. If you believe that when you put a 1 in 10 year event up in LOPA and you have, and I do this all the time, I think, yeah, that event will happen once in 10 years. It's pretty sure it's going to happen once in 10 years. Do you know your average then is close to 1 in 5? 1 in 5 once every 5 years is going to be the average of 5 year for an event that's certain to happen in 10 years. And you've just reduced your order of magnitude method by a factor of 5. And if you stack up 4 of those, you'll have reduced your order of magnitude method by more than an order of magnitude. Okay. Second example, this is from webinar 1. There was a question after the webinar about taking ERT response credit, right? These things aren't in generic data tables. I mentioned that earlier. You're always seeing this, always in LOPA, you're having to pull values in. and put them in there that aren't coming out of generic data tables. And this is based on a degree of belief. This is a perfect example. I want to take a risk reduction of 10 or 5 or whatever it is, and it's not totally arbitrary, because in this case they had done training, ERT training, and they had a history of successful trainings. And so you can see that's data. And how can we quantify that? How can we turn that into, taking a risk reduction of 5 or 10, whatever it is, we got a calculation to show that's okay based on evidence that we've been, testing and doing that. And so subjectivity is all over the place. And so the goal is not to be objective. It's impossible as humans, but it's to recognize our biases and blind spots in decision making. And I'll have another slide on that. Okay, survey says Bayes wins. The good news is there's 2 types of statistics. Yes, sorry, that's the bad news. The good news is Bayes is recognized, and you need both. You do need both, but put your effort into learning Bayesian inference, and because all of the 3 I have listed here and many others are Bayesian, are coming out with incredibly strong statements that Bayes is the only way to do, for example, probabilistic risk assessment. The new Syntev report on maintenance and failure data and using that from the operating phase is a Bayesian-based system. There was a paper written a few years ago on hierarchical Bayes that laid out given to free to functional safety of how to implement this industry-wide and how to structure it. And it probably mostly got ignored, but I'm not going to let it die if I can help that. And so, this is when I talk about Bayes and Bayesian statistics, there is real meat behind this, and it's accepted, and it's yes, it's validated, accepted, and it is what we need to be doing now. But it gets a little worse, because this slide is called Bayes rule versus Bayes rule. Well, in webinar 2, our very capable Joe Vesey presented Bayes rule as a theorem of conditional probability, and by the chain rule, you can add in additional conditions. So B conditional on A, conditional on C, conditional on Z. So it's not just 2 variables, but there's that form of Bayes rule, and then there's the form of Bayes rule that we are going to use, and that is the second one here. And let me circle it, just kind of haphazardly there. When Bayes rule is used to make statistical inferences on parameters, it becomes Bayesian. And so we're using this second form of Bayes rule. And so this is another source of confusion. I learned Bayes rule in school as a theorem of conditional probability. What's so special about it? Well, it's the second one that what we're trying to do here. And unfortunately, given the time, I'm not going to have time to go into it like I really want to. But I want to make one comment, because I told you I'd do it earlier. This term right here is called the likelihood term, okay? And if you have ever calculated an average, quote unquote, by taking, maybe the total number of failures by the total demands, or you've taken failures divided by total operating time, just a very simple ratio. So you had a little bit of data you'd pulled, and just trying to do a quick calculation. That's actually a frequentist method that falls out of this likelihood term. In fact, it's called the maximum likelihood estimate. So it's the using some calculus, you'll derive that simple ratio: failures per total demands, failures per total time. It's the parameter. You're calculating the parameter that maximizes the likelihood of seeing the data. That's what you're doing there, the maximum likelihood estimate. Okay, so that is a frequentist technique, and frequentists stop here, and Bayesians will continue and combine the likelihood with the prior. This is the prior terms. This is the analyst's prior belief. Prior means prior to data. That the prior belief that this is actually the parameter value operating in nature. Okay, that's their confidence associated with it. This is how confident I am that this is actually the parameter that we're seeing in our physical process. The posterior is here. That posterior is post data, and the idea is once you calculate a posterior on a bit of data, then you update the prior with your posterior, and your posterior becomes your new prior, and you run your Bayes engine as you collect samples. That's basically what it is doing. The denominator here is just an integrating or summing function, whether you're using discrete or continuous probability distributions, and it is completely determined by the numerator. So it's just it's math, and so just know that. Anyway, okay, I wish I could go into that a little bit more, but we got to keep moving here. Now, qualitative judgments. We do audits, assessments, life cycle activities, validation activities. And I mentioned the prior is a subjective degree of belief that's part of Bayes' rule, and it can be informed. It can be informed by generic data, generic calculations, or qualitative judgments. But it's that way that you insert that qualitative, make that qualitative quantitative is through the prior. It's the analyst's belief that this is the parameter. It's their confidence that this is the parameter that this is actually the value that is operating, that you have operating in your physical plant for this particular parameter. Okay. Okay, better decision making with Bayes. Here's some examples and what Bayes would do. I'm off my risk target by a factor of 3. Bayes says we don't need to do anything because my confidence level at that target is still acceptable. Okay, great. Next one, my risk target changed in order of magnitude more conservative. Bayes says, before we go trigger a massive capital spend to close gaps, let's evaluate how the confidence in meeting the original target has changed for each scenario. The next one, my generic SIL calc shows I have a residual gap. Bayes says, before I go spend money, I want site-specific quantification of said gap, assess and collect data over the year and run a Bayes engine, then make a decision. So all of these, interestingly, sort of tie back to LOPA, which is order of magnitude, which I think when we do LOPA, we forget that, because if we're not right on that line, then we expend all kinds of effort and capital to make that line, even though it's an order of magnitude method. We forget that as we apply it in practice. But this is some areas where Bayes can help make better decisions, especially when we have limited budgets, limited capital, competing projects and competing ideas and ways to reduce risk. It definitely is something. It's a tool. It's definitely a tool you want in your toolkit. Moving from uncertainty distributions, benefits. As I said earlier, uncertainty probability is for a future period. The probability of an event in the past doesn't exist. Probability only is meaningful for the future. Calculating uncertainty provides this forward arrow of time. Uncertainty distributions can account for increasing failure rates, age-related failures and components. Accounts for unknowns in all your parameters. Accounts for human error. Accounts for rare but extreme events, and ultimately to help us make better decisions regarding risk. And these are 3 of my favorite uncertainty or probability distributions to use when doing risk modeling. The gamma distribution for based on time, so it could be a waiting time or a frequency. The beta distribution for probability, and the log normal distribution for human error is what I normally use that for, and it's a good representation, as the other 2 are. And so Monte Carlo simulation, again, this is Excel. In Excel, you're simply taking those previous distributions that I just showed in the previous slide. You're running an inverse. You're using the inverse of those. So in other words, you're creating a random sampling to generate real value numbers of the parameter, whether it's time, failure rate, probability of failure, and you're running at least 1,000 runs, and you combine in your model, in your equations together. You come up with the answers for each iteration. You characterize that as a distribution, and then you could read the uncertainty directly from the combined model. It's the best way to propagate uncertainty in our fault trees. Our fault trees, our event trees, our QRA, Okay, so whatever model you're using with point values, this capability exists where you need it to help make better decisions ultimately. And then updating Bayes' role with cite data. And so there's something called a conjugate pairing of prior and likelihood, if you remember the equation. And it's a closed, that means it's a closed form posterior that can be calculated, for example, in Excel. And here you're just taking operational time, you're taking operational demands, through proof testing and or real demands, and you're updating the parameters of those distributions directly. And it's the easiest way to incorporate cite data directly into a probability distribution for a parameter, and you can all those questions that were asked. This is how you get to those answers, is through the uncertainty distributions with actual cite data. A couple more slides. Okay, so I'm leading now into data and reliability center maintenance. There's no such thing as systematic failure, and so this is funny because for 20 years this has been a weighted chain dragging down functional safety. Systematic failure is an artifact of hindsight bias. When you look at an event in the past, you connect the dots backwards, and you have an illusion of causality, and the randomness that was there before the event happened falls away, and you don't see it. And so there is no systematic failure, and I can't find the word anywhere in reliability center and maintenance, which is 99% of functional safety. And I don't that word. So what we need to be focusing on is age-related failures and non-age-related failures. Age-related failures are in fact not random, and we need to know when they become important. And as I say here, when we can predict when these types of errors will occur that are coupled to these failures, then we can call them systematic. Now that may be coming with data analytics. Then we may be able to predict beforehand exactly when a failure will occur, or at least know enough to prevent it from happening. Okay, have some short window we can act on, but we're definitely not there yet. So the point on this slide is instead of calling these systematic failures, these are really failure modes. And the important thing is to determine whether they truly have an age-related failure pattern or non-age-related failure pattern, which is random. And for the age-related failure patterns, those aren't random because those are coupled directly. We know when. If we know, okay, we have a failure pattern where we have a sharp increase in failures occurring after, say, 5 years. Then you know when, and those are not random. That's the point, is knowing beforehand when a failure will occur, an error will be made. Then you can call it systematic, or more appropriately, an age-related failure. Okay. Data collection 101. The good news is if you're testing and performing PMs, you're already collecting data. The bad news is it can be complicated and it's very human intensive. I mean, we're not even, I mean, yeah, you're talking about an entire, in a large organization, one person or maybe more just doing this. And so, yeah, it can be a high bar, and it can be definitely a hurdle. And now the good news is if you're doing RCM anyway, you may be a long way toward this related to functional safety and some of the issues I'm bringing up. In fact, functional safety is 99% RCM, and that goes back to the frustration of systematic failure. I don't see it anywhere in RCM. I don't know how that term came up and why we still use it. It's dragging us down. We need to stop. Now, also in terms of human intensiveness, someday maybe this data analytics revolution will help remove some of that human intensiveness. It's not right now. It's probably worse. We need more humans now to do machine learning and setup. We actually need more humans. Okay, so let me say the small data problem. This is a slide on how much data do we need to prove a claim. Of course, on the site, we have a problem with small data. I haven't mentioned that yet. So here's a few bullet items on some good rules of thumb, so to speak, on how much data you might need. And these are broken up generally in terms of frequentist and Bayesian. So let me get my little pen working here. So above this line to the top is going to be these are frequentist concepts up here, and below the red line you can see Bayes kicks in here, and so you can just read that, take a screenshot of it. I'm running out of time here, unfortunately. And my top 10 low-hanging fruit. Okay, track time and service. You're looking for age-related failure patterns by failure mode and by equipment type. That's some of the complexity. This is data visualization, not calculation, but you're trying to get at items 1 and 2 go together. You're trying to get at that useful life period to verify it. You have a value that you've used through design that's come generically. Now can we validate it with site data? It's a safety and a cost issue. It's both. I see really short useful life periods. Are we really doing scheduled discard maintenance on these components and just putting new ones in? I don't know. So I'm sure some people are, some people aren't. But that would be where I would look first, is confirming those age-related. Age refers to how long the device has been in service. Okay, and so after a certain amount of time in service, if for age-related failures, you're going to see that sharp increase in the conditional probability of failure. But again, it's visual. You're not calculating anything. The third one up here is we're not trying to redo SoCalcs, and we're not trying to throw out the generic data by any means. You put a lot of effort and a lot of energy and a lot of cost into that. You're looking first to confirm or not your generic data, your generic priors. Fourth, it's much easier to update, to run Bayesian updates on proof test pass-fail in terms of PFD average versus failure rates. Failure rates opens a whole can of worms, and it just, the first thing is just how to define it. Conditional probability of failure, which is a failure rate, versus, for example, mean time between failure, the inverse of, which is a failure rate. They're not the same thing. Don't forget to, number 5, don't forget to assess your initiating cause, your demand rates. This is a huge source of uncertainty, and where you can be off orders of magnitude. And this comes right out of LOPA. Define upfront what it means to be identical versus similar data for data pooling. When you see the word similar in Syntav or anywhere in these functional safety standards, they really mean identical. To make valid comparisons, you should be using identical data, and anything off of that is going to produce uncertainty. And so you need to make a decision up front: what is similar, what is identical, and how you're going to treat it. Develop procedures for how you evaluate assumed versus actual reliability parameters. Put it in the SRS. We need to start creating this in the SRS to show how to do this. There are some statistical techniques like Bayes. Some hypothesis testing is possible too with frequentist methods, but it's very accessible, and we need to start doing it. Baby steps, start small. Even a little progress will greatly facilitate the coming data analytics revolution in process safety. Even the little bit we can do regarding this, we should do it for that reason. Okay, well, if you have stayed with me this whole time, I do appreciate it. Okay, let's get to the question. Okay, the first question here is posted by Anonymous. Can you explain that 1 in 10 to 1 in 5? Didn't quite follow that. Okay, that's a good question. That was on the slide from talking about LOPA land, and it's a result of the Poisson distribution. So, which is a discrete distribution, and it's easy to use in the sense that you're discrete, so you're using discrete numbers, and you can kind of plug and play with that. But that's the result of the Poisson, and what it's saying is, if you know your average rate, you can calculate how many events, the probability of having an event over some time interval. Again, that's what the Poisson gives us. So this was a little trick or tip I picked up, of all places, from Trevor Kletz. Trevor Kletz, just a little aside here, he's 99.9999999%, safety, process safety, functional safety even. The one thing that I think I have never seen Trevor Kless write about was Bayesian statistics. But anyway, that's an aside. But I picked up this trick from him. So if you assume an average event rate has an average of every 5 years, you can just use the Poisson distribution to show that after 10 years, you're not guaranteed to have it, but it's 90%. And then if you go another time period, then you're well over 90% certain that you should have seen the event by then if your true average was 5 years. So that is an answer to that question. Now, I actually misspoke a little bit. It doesn't reduce by a factor of 5, it reduces by a factor of 2. But the point's still there. If you have that same bias in your thinking, then after a few layers of protection are put in, you're still exceeding order of magnitude, but it's a factor of 2. Okay. Hopefully that answers that question. Aaron writes, chi-square distribution question. What kind of technique is using chi-square distribution to calculate confidence intervals? Good question, because the chi-square is the go-to of functional safety. It's the go-to of SIS engineering. Now, very interestingly, the example statistic I gave of the maximum likelihood estimator, and I said frequent to stop there, right? Well, if you're a good sys engineer, you won't stop there, and you'll kick that average out and do a chi-square distribution with your data sample, and you'll calculate confidence intervals, and that's where that chi-square comes in. It comes in after you do a maximum likelihood estimator. Now, the only problem, and so this is some of the limitations of frequentist methods. The likelihood is not a valid probability distribution. That's why they call it a likelihood. And so a frequentist has to then kick that answer out into another probability distribution. The benefit of Bayes' method is, of course, you keep the likelihood there, and then it is a valid probability distribution. The posterior is, in other words, from Bayes' rule, the posterior is a valid probability distribution once you combine it with the prior, divide by that normalizing factor in the denominator. That's what it's doing. It's turning Bayes' result into a valid probability. So you don't need an artificial chi-square distribution. The chi-square distribution is it's called the variance distribution. It's not even a distribution of your parameter. It's what it is if you sampled a normal distribution, it's a distribution of the variances that you would get if you sampled a normal distribution and you created a distribution on the variance from a normal distribution. It has nothing to do with the parameter. Now, that's some of my passion coming through. I say it has nothing to do with the parameter. It's better than nothing, and so just take that with a grain of salt. I'm not saying it's not a valid way to do it by any means, but it goes back to that it may not mean what you think it means kind of concept, and make sure you understand what statistics mean that you're using and what you're getting and what the implications are. The next one here, if you're parameterizing Monte Carlo, this is from Bob, by fitting the results to, say, a gamma distribution, which is what exactly I talked about. Is there generally any bias related to small number statistics of the number of Monte Carlo runs, or does a minimum of 1,000 runs pretty much remove any potential bias? You can, in Excel, you can run 1,000 or you can run 10,000. So it's a matter of seconds. So, but the bias, yeah, that's a good question. So I would answer no. You can run maybe 1 million runs, and you can never be absolutely certain that you've removed all bias other than pure random bias just from that distribution. You certainly remove from running more Monte Carlo runs. But the real bias that we're worried about is kind of some of the examples I gave, and it's that epistemic uncertainty caused by the bias of human judgment. That's much harder to get at, and that's not being sampled in a Monte Carlo. You're not getting any samples of that. And so that is a fundamental uncertainty, and that also goes back to Taylor, discusses that extensively. So that is that's hard to remove because it's hard to find. Okay, hopefully I answered that. Okay, Anonymous, how do you account for equipment replacement, improvement, better maintenance, et cetera, that affect failure rates? Well, the main thing there is we assume age-related failures in functional safety. And my comment was, which is fine if the device and equipment truly have an age-related pattern for a given failure mode. Every failure mode will potentially have a different failure pattern, but we need to be performing scheduled restoration or replacement, discard and replacement. But that doesn't mean you can't calculate a failure rate from that, and you still have a mean time between. I would suggest for this. Look at the book that I had referenced there, the RCM book. If you're a functional safety person and haven't dabbled in that book, that will be a game changer for you. So I would recommend to grab that book, and that your question is discussed in there, and we'll do much more justice than me trying to answer it. Okay, anyway, that is our last question, and we are at our full hour. I do appreciate the people that hang on even through the questions. And everybody have a good rest of the day, and we'll talk to you all later.